So my name is John Mount, and this is Dr. Nina Zumel, and we're going to be presenting some of our work on dealing with messy data, which it's kind of a funny thing to say. Is there any kind of data other than messy? So you don't really need that word. So who are we? Well, we're data scientists that normally work with R, and we have with us the fresh new version of Practical Data Science with R, second edition, which Amazon just admitted exists today. So they were ghosting us up till now, so today's a good day for us. If you don't exist for Amazon, you don't exist at all. However, so for years, we've been using this package in R, and we've built a new Python version that is Pythonic. It's not an R package in Python. It's an actual Python package. So what we're going to discuss with you is first the problem. Why do you have to prepare data at all? Why can't you just use data as it comes into your system or your ingest system? And then we'll show modeling with and without vtreat. And obviously, we're going to show that it's very bad not to use vtreat, that we're huge fans of our own package. And then we'll describe the package, and we'll show some of the technology that makes it actually work. Because it turns out once you touch the data, everything's your fault. And you have actually a really great opportunity to introduce overfitting and nested model bias if you don't do something very clever, which Nina will describe. And then we'll get to some references. So why do we prepare data? Well, basically, often the data is quite dirty. It'll have missing values, strange categorical variables, string variables, that new strings occur during application that you didn't see during training. Once you touch real world data, it'll do anything to hurt you. The also thing is, especially in scikit, or the Python scikit world, most of the machine learning algorithms expect a pure numeric data frame, that they don't want any categorical or string valued variables left around. And we want to get into that format in a systematic way. So again, you can't automate data science, that you have to actually care about and look at your data. We're trying to automate the simple steps so you have more time for important domain-specific interventions. So again, as I said, typical data problems, missing values, categorical variables, those are variables whose values are strings or interpreted as strings, and categorical variables with very many levels, such as zip code, which has 70,000 possible levels, and that's very statistically inefficient to deal with those directly. So as in our example data set, we're just going to kick something nobody cares about. It's the KDD Cup 2009 data set, and it was to predict churn or account cancellation in a credit card account. And the data was truly horrific. Just a data summary, it was 230 columns with no data dictionary, so they never said what any of the columns were. They all had cryptographic names. There were lots of variables, 50,000 instances, which is not a lot in our day and age. It had both numeric and categorical variables. Most of them were completely infested with missing values, and many of the categorical variables were high cardinality, which means they took on a lot of cryptic different values. And again, no data dictionary, no way to roll up or join into anything useful. And it was an unbalanced task also, just as churn is the cancellation of an account, and around 7% of the people in the observation window did this. This is what happens if you throw the data at XGBoost as is. And basically in red, we have the exception that was raised, and that XGBoost said that some of the variables were of types I am unwilling to deal with. And again, that's not a mathematical issue. You can do tree-based methods and boosting on categorical variables, but with this type of API, especially, this is not scikit-learn, but with scikit-learn, you're not allowed to have non-numeric columns, so you need to prep the data. Now, even if you fixed this, you would then run into your next problem that you still have missing values. Then you'd run into your next problem that even though you've re-encoded some of the categorical variables, you've blown up your data set into hundreds of thousands of columns when we only had 50,000 rows. So, and then you get the rare levels and novel levels, which are statistically, even if you have enough data processing memory to deal with them, they're statistically poison anyway. So, grab bag solution, yeah, scikit-learn, one hot encoder plus the simple imputer plus maybe Keras layer embedding to eliminate. No. So why would we not do that? Lots of steps to manage, may not be statistically efficient, and possibly subject to this sort of overfit bias that a lot of people haven't considered very deeply, though the stacking community has thought about this quite deeply. So basically, there's got to be a better way. And in R, prejudiced mind, that better way is our own package vtreat. It's easy to use, it has known good performance, and it has citable documentation. So you can add this to your methods section, and you're quite far along in your documentation. Here is vtreat working on the KDD 2009 dataset. I'm sorry, we will put up all these slides on the WinVector blog. So all you need to do is search for WinVector blog, and we'll have the entire deck up with all URLs. Should have said that earlier. So basically, all we need to do is call fit transform, fit underbar transform. That's it. We try to do a scikit-learn pipeline style interface, call fit underbar transform, not fit and transform, but always the underbar form. And what that gave us was an AUC on held out or test data of 0.73. Which is abysmal, but for this problem, in the ballpark of the winning solutions. They were in around 0.74 to 0.6 after many days of effort. So this gives you a fire and forget that we used vtreat with no hyperparameter tuning, we used XGBoost with no hyperparameter tuning, and in 10 minutes, we're in the ballpark of winning, which again, life isn't a Kaggle contest, so in the ballpark is business good. So there's the results. Sorry, I spoke ahead of my slides. And again, here's the reference to the contest. All these links are in the slides, which we will share on the WinVector blog. So the vtreat goal is to be ready, faithful, and reliable. So basically, the data needs to be converted into a ready-to-use data format, which means all numeric columns, not an obscene number of columns, and the data is not encrypted. You haven't done something completely strange that the machine learning algorithm has to work hard to overcome, that the information is there, but at the surface level. By faithful, we mean most of the information in the original data set is still there. We can't preserve all of it for the high cardinality categorical variables, but we're going to preserve a lot of it, and we're going to preserve all the common information. And by reliable, we mean it doesn't introduce additional problems on its own, in particular the nested model or stacked model bias, that it has a very sophisticated cross-validation method to make sure we don't run into that. So the main benefit of vtreat is it's built on top of pandas, so it reasons in terms of column names, which is, again, given our R background, we like column names. And what it gives you also, which using one-hot encoder alone doesn't, is a concordance between the original variable names and the new variable names. And again, the first 3 columns of this score frame, which is a part of the vtreat side effects, is what's really interesting. The original variable says I was a variable named X. I produced 2 variables, one called X, one called X is bad. I'm reading off the first 2 rows. The X is bad is a missing indicator, and the X is a clean copy. So the third column says what was the treatment strategy that built these derived variables. And this lets you then attribute new variables to old variables. So with that, I'm going to switch over to what does vtreat do?
Okay, thanks, John. Now that John has given you kind of a quick overview and introduction to why you might want to be interested in vtreat, I'm going to go into a little bit more detail about how it actually works on the data. So the first thing that vtreat does is that it repairs numerical variables that have missing values or other problematical variables like non-numbers, replaces those problematical variables with more benign stand-ins, by default the observed mean of that variable, but it can be other values as well, like the median or the min or the max, or even a constant. In addition to replacing problematical variables, vtreat also adds an additional variable, an indicator variable that John pointed it out. It's called the isBad variable, and that marks where these problematical variables were replaced. Adding this extra column makes this particular transform basically invertible, which means that we are preserving as much of the data in the original variable as was there for use by the downstream modeling algorithms. And if any of you were at the auto-impute talk yesterday, you can also think of this particular transform as being a compromise between treating missing variables as missing at random and missing systematically. Often you don't know why you have missingness in your data, whether it's random or systematic. And so vtreat just kind of splits the difference and treats it like it's both. Again, for downstream modeling algorithms to kind of sort out and figure out what's going on. And in fact, we find in practice that these isBad missingness indicators are sometimes even more useful than the original variable itself. And the reason that that might be is that often the data that you're collecting in order to do your job comes to you from a variety of different processes, and sometimes the difference in these processes manifests itself in missingness in some of the data. And that's kind of an implicit kind of information that's in the data. And by adding an explicit indicator variable, you've made that data explicit and therefore more accessible to downstream modeling algorithms. So consequently, these is-bad indicators can be sometimes the most informative variables in your data. The second thing that vtreat does is to encode categorical levels as indicators. This is pretty straightforward. Essentially, what vtreat does is similar to calling scikit-learn's one-hot encoder with the parameters drop equals none and handle unknown equals ignore. For those of you who are not familiar with handle unknown equals ignore, it allows the one-hot encoder to gracefully handle novel levels. So for example, if you have a data set of customer data and one of the features that you want to use is the state of residence, and let's say that the training data has only customers from 4 states, California, Nevada, Oregon, Washington, the one-hot encoder and vtreat will basically turn those 4 states into 4 indicator variables. And those are the only states that the model, when you train a model on that data, that the model will know about. So you build a model, you want to apply it to a new set of customers, and bingo, some of these customers come from Wyoming, which the model has never seen. Now, if you had built this model in R without vtreat, and remember, vtreat was originally an R package, the R model would crash on seeing customers from Wyoming. And if you build it in Python without using the proper unknown handler, so if you use the wrong parameters for one-hot encoder, the model will also crash. If you use the right parameters, or if you use vtreat, what happens is that novel levels are treated as basically no level. They're encoded as all zeros with the indicator variable. This allows the model to continue to process customers from Wyoming and South Dakota and any place it's not seen without crashing, which is a good thing. The primary difference between what one-hot encoder does and what vtreat does is that vtreat does not, by default, dummy encode all of the observed levels of a variable, of a categorical variable. It only encodes the most frequent ones. And the reason it only encodes the most frequent ones is because vtreat is trying to explicitly manage dummy variable blowup from high cardinality categorical variables. And by a high cardinality variable, a categorical variable, I mean a categorical variable that has several hundred or maybe even thousands of possible levels. Zip code is the classic example. John brought it up. There's something like, he said 7, I forget what number he said, but when I looked it up, there's something like 42,000 zip codes in the United States, almost 3,000 of them in California alone. So let's imagine that you are trying to build a model to predict home sale price for houses in California. And one of the features that you want to use is the zip code of the house. So even if you're just looking at California and not the rest of the country, just from this one feature, zip code, you can potentially have almost 3,000 variables. And that's before even considering any of the other variables that you're looking at. Having too many variables in your data is a problem for a couple of reasons. One is that too many variables can be a computational problem for a lot of machine learning algorithms. And more significantly, if you have too many variables with respect to the number of rows that you have an overly wide data set, then you're going to have an under-constrained problem if you're trying to use a more complex machine learning algorithm, which usually we are these days. And the easiest way to accidentally have an overly wide data set is to have a couple of variables that are categorical variables that are very high cardinality, or even to just have a lot of moderately sized categorical variables that together add up to a lot of indicator variables. So you want to manage that. vtreat manages it one of two different ways. One is, as I mentioned, it only dummy encodes the most frequent levels of a categorical variable. So basically, it only dummy encodes levels that occur more frequently than some user-defined thresholds, say levels that only occur in more than 2% or 1/50th of the data. And the reason you want to do that is that limits the number of dummy variables that are created per categorical variable. So if we set the threshold to 2% and then we go do the vtreat dummy encoding of zip code, what we will get, remember 2% is 1/50, so what we will get is at most indicator variables for the 50 most common zip codes in the data, and probably fewer than that, depending on how the data is distributed. So this prevents the number of dummy variables from blowing up. Now, if you've got 3,000 zip codes in California and you've got 50 dummy variables, there's still a lot of zip codes you haven't encoded, which are probably in the data. So in addition, vtreat also converts categorical variables to a single informative numerical variable that takes into account all of the observed levels. And this encoding is called impact coding. And what impact coding is basically building a lookup table of conditional outcomes. So going back to our zip code example, you take all the zip codes that are in the training data, you find the average home price for that zip code, and you also find the average home price for the entire data set. So the impact value, the impact coding, is the difference between the zip code average and the global average. And that's why we call it an impact variable. So basically, if you've turned these zip codes into a numerical value, if the numerical value is negative, that means that that zip code has an average home price that's lower than the global average. So you can kind of think of it as that zip code has a negative impact on home price. And then if the zip code has a positive impact variable value, then its houses are more, have a higher sale price than average. So that zip code has a positive impact on home price. And so then to impact code the zip variable, you just convert all the zip variables using this lookup table to the appropriate value. And when you're doing this to future application data, you run into a zip code you've not seen before, you simply encode it to 0. Now, the issue with impact coding, it's very concise, and it does preserve a lot of the data that's a lot of the information that's in the original data. But unlike simpler transforms like missing value imputation and one-hot encoding, impact coding, to impact code a variable, you have to look at the outcome. Basically, an impact code is a one-variable model for the outcome in terms of, in this case, zip code. So if the problem is, if you use the same training data to learn your impact code, then impact code your zip code, and then use that exact same set of training data with this new synthetic variable to train your downstream model, you're going to introduce bias, because the impact code has basically peaked at the answer. So the downstream modeling algorithm will be biased in favor of that impact code. It will look more informative than it really is in reality. And that leads to overfit, sometimes some very bad overfit. So you want to avoid that. The proper way to impact code is to make sure that you're learning your impact codings on a separate data set from what you use to train your downstream model. And the easiest way to do that, if you have enough data, and it's what I'm showing on the diagram on the right, is you take all your training data and you split it into 2 sets. Let's call it the calibration set and the training set. You use the calibration set to learn this lookup table, this impact coding lookup table, with all the conditional outcomes. You throw away the calibration set, you take the other set, the training set, you impact code the zip code of that set and do all the other vtreat treatments, and then you use that treated data to fit your overall model for, in this case, home price. Because you haven't reused the data, you will not have this nested model problem, and you will avoid that potential overfit. Now, if you don't have enough data to split into calibration and training, then you have to use cross-validation methods to create what we call a cross-frame that also will avoid these overfit problems. Cross-frames aren't unique to vtreat. I mean, basically, this cross-validation method is also the proper way to do stacked model ensembles as well. They don't call it cross-frames, but it's the same idea. So for the purposes of this this part of the talk, you're going to see the diagram say model. When I say model, what I really mean are those lookup tables for doing the impact coding, and the model predictions are really the impact code. So the idea for the cross-frame is that no row should be processed by an impact coder that it was included in the construction of. And I realize that that's kind of a confusing sentence, and that's kind of a messy diagram, so let's just kind of walk through it more slowly. You have your training data. And for our interests, what we're most interested in the data row is the zip code of the row. You partition the data into k folds, in this case, 3 folds. You take folds 2 and 3, and you build a model or a encoding lookup table, and you use that lookup table to encode the zip code in fold 1. Then you take folds 1 and 3, you build another lookup table, and use that lookup table to encode the zip codes in fold 2. And then you take folds 1 and 2, you build a lookup table, and you encode the zip codes in fold 3. So now what you have is, on the far right-hand side, what you have is a set of encoded zip codes for your entire training set, where every row was encoded by a lookup table that it was not involved in the construction of. So basically, you've simulated splitting the data into a calibration set and a training set, only you've done it in a much more statistically efficient manner so that you are now able to use all of your training data to train your downstream model safely. Okay, trying to implement this cross-validation can be a little bit of a hassle, so luckily vtreat will do it for you. Vtreat allows you can use vtreat either with a calibration and training set method or with the cross-frame method. If you have enough data to split into calibration set and a training set, then you fit your vtreat treatment plan on the calibration set, and then use that plan to transform your training set, and then that treated data is what you use to train your downstream model. If you do not have enough data to split into calibration and training, then you call fit underbar transform on all of the training data, and that will simultaneously fit an appropriate treatment plan and create a cross-frame, which again will be safe to use for training a downstream model. The important thing to note here is that calling fit and then transform on the same set is not the same as calling fit underbar transform on that set. That's why I've crossed out what I'm calling the naive call on the top. If you do fit and then transform on the same set, unless you are going to throw out the impact variables or any of the y-aware treatments, that's not a good idea because you will run into nested model bias. And then once you've got your treated training set, training data, and you've fit a model, and you want to apply that model to new data, you simply take your existing treatment plan, you transform that new application data, and then you can apply the model to it. So basically, all of the vtreat processes that we've discussed in this talk are available to you in basically 1 or 2 lines of code. Easy peasy. So that's basically a quick overview of what the most basic things that vtreat does. So let's go back to the KDD 2009 example that John talked about at the beginning of this talk and sort of see what happens if we try to use vtreat to treat the data and build a model with and without the cross frames. So just to point out to you why the cross frames are important. So first we'll try treating the data with vtreat the naive way, where we call fit and then transform on all of the training data. This is the naive way, which again, you're not supposed to do. You take that data, the treated data, and you fit a model. You try to evaluate that model that you've learned on the training set, and it looks fabulous. This model appears to have, on the training data, an AUC of 0.95. And you're like, yay, did a great model. But you take this model, and then you try to apply it to holdout data, and it fails. Basically, on holdout data, you now have an AUC of 0.6. So what you see here is that the model that you fit without the cross frame is overfit and does not generalize well to new application data. So let's try to do it the proper way with fit underbar transform, which produces a cross frame, and use that cross frame to train your model. That produces a model that gets an AUC of 0.74 on the training data, and an AUC of 0.73 on the test data. So basically, you've managed to avoid the overfit, which is the goal, and you've also started with a kind of, as John said, 10 minutes, you've got a basic model from which to start improving to try to get better performance. So to wrap all of this up, what we've presented today is our vtreat package, which is an easy-to-use, statistically sound process to prepare data for machine learning. The prepared data is guaranteed to be entirely numeric and have no missing values, so it's safe to use in downstream modeling algorithms. Again, as John said, having automated data treatment is no substitute for actually getting your hands in the data and getting to know it, getting to understand what those features are. But what we would argue is that the steps that we've talked about today, dealing with missing values, dealing with high cardinality variables and novel levels, guarding against novel levels, these are all kind of grungy data steps that you have to do for basically any machine learning problem. So basically what we do is with vtreat, you've automated the grungy common data steps, which leaves you, as a data science, more time for the creative steps, the fun steps for developing high value ideas and feature engineering or whatever that are specific to your domain or your problem. And everybody wants more time for the fun stuff, which is kind of a great idea, great reason to use vtreat. References. We have on the WinVector blog, we will post these slides to the WinVector blog. And so you'll have all these URLs. We have a couple of old blog articles on the ideas behind impact coding. So you can read about it in more detail than I've talked about today. We also have a paper on archive.org that discusses, again, all of the ideas that we've talked about today and probably a few more in a little bit more detail if you're really interested in kind of the guts of what vtreat does. The vtreat paper is written with respect to the R implementation, but the ideas are the same in both implementations. We also have GitHub repositories for both with additional documentation, calling interfaces and APIs, et cetera, for the R version of vtreat, which is also available from CRAN, or downloadable from CRAN, and the Python pandas version of vtreat, which is installable from PyPy. And that is my talk, our talk. Thank you, and we will entertain questions.
I noticed that a lot of the solutions that come up make some assumptions about the skew of the data a lot, like a lot of averaging or even lack of meaning was happening. How do you recommend before you use the tool, if you know there's potential data skew or you think there's data skew based on the results not matching well, to handle that before you use the tool? Or is there a good way to integrate, like implementing alternative algorithms to do the averaging solution into something that might, like maybe you have a Laplacian or something like that, so the average doesn't really put you in the right spot?
If you have, say domain knowledge about what the transform should be. So for example, if you happen to already know that the variables are, say, log normally distributed and the mean is not appropriate, you can, by default, vtreat uses the mean, but you can fill in any summary statistic that's a one variable summary statistic. We don't do a lot of sophisticated, so you can use the median if that's appropriate, the mean, the max, whatever you happen to calculate, or a constant. I would say if you wanted to do, say you wanted to use auto-impute or something like that, I've thought about this for like a grand total of 2 seconds now, but I think if you wanted to use auto-impute, you might be better off using, since it deals with missing values first, you'd want to do that first. I believe auto-impute does not make any assumptions about missingness at random versus missingness completely at random versus missingness systematically. So, up to you, but you may want to still additionally keep some information about where those missing values originally were so that you can, again, hedge your bets.
Yeah, I'd like to swoop in. I saw the auto-impute talk, and it was excellent, by the way. So it lets the user control what they want done, whether it's missing at random or missing systematically. And yeah, so the vtreat will accept as user code any one variable imputation method. However, if you want to do something smart, like use the other variables to reason about it, you would want to do that exactly as Nina said, as a pre-processing step. Now again, one of the vtreat design principles is nothing's our fault because we're not the last one to touch the data. The downstream model is, and we gave it that indicator variable. So if wishes were horses, it would fix everything. So, but again, we're very sensitive that if you want to do something intelligent about the missing values, or joint about the missing values, you'd want to use something as a pre-processing step, like Nina said. vtreat's principle is it treats the variables fairly independently. It says any joint property of the variables is a modeling step, so it tries to stay away from that, leaving that for you. Really good question, though. And we've recently put in this function thing because people are like, mean is so inappropriate for even log normal distributions. So you can type in a user function like median and you'll be fine.
Hi, so I use a lot of time series data, so I really love the cross-fold idea, but my issue with any cross-fold is that you end up training on past data.
Yeah, I really want that. Nina and I are doing a lot of teaching now, and for people that have not done time series data, they're like, well, you just do random split, and you're like, no, that's not how time works. That training a stock strategy that uses Monday and Wednesday's data to trade on the intermediate Tuesday, that doesn't work because it doesn't have knowledge of the future. vTreat accepts as its cross-validation arbitrary code. So you can say, I want a time-ordered split with respect to all the splits. Yeah.
It's already implemented in Python.
Yeah, that's implemented in Python. So basically, in both the Python and the R vTreat, Nina's the main scientist, I'm the main coder. So when she says, is that implemented, it means have I done what I promised her? But yeah, both in R and Python, the cross-validation strategy is accepted as an external function in R and object in Python, which then you could say, this is what splits make sense to me, and therefore it'll work. And it's also touched on in the earlier drafts of the paper, but it was weird. Nobody that didn't work with time series understood that there's more than random splits for cross-val. It was just frustrating trying to explain this to people. But really good question.
If that's it, then thank you very much for attending our talk.
Yeah, and we have the slides up on the WinVector blog, so just Google WinVector blog, and it'll have all those URLs. And Nina has written a lot of documentation for both versions of the package. Basically, there's this directory tree called examples, which shows how to get from a task to end. And then we actually have to know what the heck it's done to our data. That's what the more technical document's for. There's always this problem. If you describe an implementation, what's the benefit of the implementation? I just went through all that. So we've tried to separate that and make them both available. Thank you again.